Hello student, welcome to section 8.5 from the Nelson textbook. So here I'm going to be solving some questions for you and I hope that you get some benefit from it. So we're going to start off by looking at question number 2. Number 2 says, an aircraft is flying at Mach 2. What does this mean? First, let's look at the formula and then we're going to be able to explain just from the formula itself what this actually means. So the formula, we have the Mach number, and then we have the airspeed of the object divided by the local speed of sound. So really, Mach number looks at a ratio of how quickly an object is moving in that particular area, because the speed of sound, as we saw, it varies by temperature and the number of particles. There's a lot of factors that go into actually measuring the speed of sound, but in this course we're just taking the temperature measurements at least into consideration. So we can say that depending on how quickly an object is flying, we can measure the Mach speed number based on the local speed of sound. So we can rewrite this formula by considering the aircraft in this question. And in this question, that aircraft is flying a Mach number 2. So we write 2 the aircraft over the speed of sound. So in other words, if we're going to multiply both sides by the speed of sound in the denominator, this will give us twice the speed of sound equals to the speed of the aircraft, which is what Mach speed number tries to tell you. So like, oh, this object is traveling twice the speed of sound, you might have heard. So that means it's traveling twice the speed of sound in that particular region. Or if Mach number is 1, then you can say that the speed of the aircraft equals to the speed of sound. So people always want to go faster than the speed of sound, and it was really cool because when we first broke the sound barrier, it just means that an object was traveling faster than sound itself. That's pretty cool. For question number 3, we have an aircraft is traveling at Mach 0.83 in air at 10 degrees Celsius. What is its speed in kilometers per hour? Wow, this is actually pretty tough. But first, let's start off with the formula. So the formula considers the Mach number, and is looking at the speed of object in the air. And it takes it as a ratio to the speed of the local sound, or you could just say the speed of sound. And in this case, we got that the Mach number is 0.83. So 1, when Mach number is 1, that means that the speed of sound is the speed of the aircraft. So if the number is less than 1, then that means that the aircraft is not yet reaching the speed of sound. So it's just a little bit off. So if the speed of sound, maybe it's 343, 341, that means that the object should be traveling 340, 240, we don't know. So in this case, we suspect that the number should be less than 300. So let's double check here by putting in what we were given. So the speed of the aircraft and the local sound speed, so V sound. Like before, we're going to rearrange for the aircraft speed by multiplying both sides by the speed of sound. So the speed of the aircraft is 0.83 the speed of sound. So a fraction of the speed of sound. That's why we said is less than, because that fraction is a number less than 1. So now, in this case, they also gave us that the local temperature in air is 10 degrees. So from the local temperature of 10 degrees Celsius, we can calculate the speed of sound in that local temperature. So we're going to have to use another formula. So this is very helpful to have a formula sheet, right? So you could check out the link if you want to have one for yourself. So V sound equals to 341.3 sorry, meters per second plus 0.606 meters per second per degree Celsius times temperature. Now let me double check that I have this formula correct. .4. Okay, so I made a small mistake. So that's why having the formula sheet is really good. 331.4 meters per second. The rest is good. All right. Now, what this formula tells you is that the speed of sound varies by temperature, and for each 1 degree Celsius of change, it's going to increase by 0.606 meters per second, or the other way around if you decrease it by. So in this case, let's calculate the temperature at 10 degrees Celsius. So we just sub it in the values into our formula. So notice that the units of degrees Celsius cancel out, which is what we wanted. And this gives you 331.4 meters per second plus 0.606 meters per second times 10. Right, if it's by 10, just multiply the 1 decimal. If it's by 10, just move the 1 decimal place by 1. And then let's do the sum. So let me take out my calculator and check. We get 337.46 meters per second. And remember, this question was asking us to calculate the speed of the sound of the aircraft. No, it's asking us to calculate the speed of the aircraft. So once we have the speed of sound of the local air, we're going to sub it into the formula that we were using before with the Mach number. So let's make that substitution now. So the speed of the aircraft equals to 0.83 times the speed of the local sound, 337.46 meters per second. And we get approximately 280.09 meters per second. Which is what we expected, right? Because we wanted because the speed of sound wasn't quite met, because if the Mach number is 1, that means the speed of sound equals to the speed of the aircraft. But if it's less than 1, then the aircraft speed is not quite as high as the speed of sound. So that's why it's still a high number, but not the 331 threshold or 337 in this local sound. Now, the question did ask me to change it to kilometers per hour. I'm sure you can do that yourself. So I'm going to skip that part. Okay, so the next question, let's see. Explain why the speed of sound varies in different materials in table 1 on page 395. So I took the liberty to just paste it here so you can see it for easier access. So let's try to analyze this table. And we want to explain why the speed of sound varies in these different materials. But even within the same material, if we just consider air, notice that for 20 degrees is 344, 0 degrees 331, and negative 20 319. So as we suspect, the speed of sound gets higher as the temperature gets higher as well. So we could write this down. So as the temperature increases, the speed of sound increases. In air as the medium. Right, and that would be vice versa. So if you decrease the temperature, then the speed of sound gets lower. Now remember, sound is just an example of waves, and waves are a transfer of energy. And temperature is a measurement of the motion of particles. So if the temperature is really high, the particles are moving about really quickly, and the likelihood of collisions is much higher. So when the particles collide, that's when they exchange energy. And if we can increase this number of collisions, then you can increase that rate at which energy gets transferred, which is what we mean by the wave speed. So this is why the speed of the sound increases with increasing temperature, because with increasing temperature, there are more collisions. More collisions means more transfer of energy. And if the transfer of energy occurs quicker, then the speed of the wave, which is the transfer of energy, happens at a faster rate. So let's try to put that as a single note because you might have gotten lost. So higher T implies higher motion, which means increase collisions. And if you increase collisions, then you increase energy transfers. Which energy transfers is wave, the speed of the wave. So that's one way you can remember this, okay? Now, this table is still not finished. There's still more information to be gathered here. Notice instead that if we look at glass, steel, water, wood such as maple. Oh, the name of my dog is Maple, but in Chinese it's Jia. That's interesting. Maybe not so much for you. But anyways, what do we notice here? Well, glass is very dense material because it's almost like sand being very close together. And then wood and steel have less density. So maybe if we consider only glass, steel, and wood, so glass higher than steel, higher than wood. By higher, I mean that the speed is higher. So let's have high speed, low speed. So why does this happen? Because the speed of sound depends on the medium only. And the medium, we looked at temperature, but then we also look at the density of the medium. So in this case, glass is actually more dense than steel, and it's more dense than wood. So the more dense the material is, by density we mean the number of particles in an area. So if the particles are closer to each other, when they collide, it occurs more frequently because they're already very close to each other. So they just have to move a little bit, then they collide, which we said transfers energy. So this high speed to low speed is because of the density of the material. So we can think of this as high density and low density. Now the one that's interesting here is water. It's kind of like the odd one out, right? So notice that in water, it is less than the previous three. And it's also due to density, because in solids, we have the density much higher, but in liquids, the particles are moving about more in that particular medium. So this means that the density of water is even less than of solids. So this also depends on the state of matter. So solids travel energy much quicker than liquids. So this is even lower speed. And we can account for this for state of matter. So what do we mean by state of matter? We can say that solids transfer speed of a wave much quicker than liquids. So you see how we can change the speed of a wave by changing the temperature, changing the density, or the state of matter in this case. All right, so hopefully you're enjoying the lesson so far. Well, not the lesson, but the homework help. And normally, you know, you get a tutor, but then I know with the conditions of the world, it's not so easy to find tutors. So I'm trying to help you out by giving you this so you could access online and for free as well. So make sure you put a thumbs up, help support my channel. I really appreciate that. Now let's look at question number 5. In your own words, define sound intensity, loudness, and decibel. So I'm going to set this up in 3 different columns. Now, to understand sound intensity, it will help to get the formula, but I know that this lesson, they didn't give you the formula in this section of the book. They only gave you the units. So the units are measured in watts per meter square. So we kind of have to be doing some detective work and figuring out what the formula might be. So if the units are watts, that's measuring power. And if the units are meters square, that's a measurement of area. So this is actually the formula for sound intensity. So it's kind of silly that they don't give you the formula, but this is the formula for this particular sound intensity. And more commonly, the sound intensity, you could think of it not as power, because power is a bit tricky, because power is the amount of energy transferred in a given time period. So you can almost think of this as energy passing through a given area. So now, what are some ways that we can help to define sound intensity? Well, by first looking at this formula, we can look at the conditions, how we can change sound intensity, and then try to get a better idea from it. So let's see. As energy increases, the sound intensity will increase. right? Because of the equation, they're directly proportional to each other. As you increase the energy, you're going to increase sound intensity. The reverse will be true too. If you were to decrease the energy, then that means that you decrease the sound intensity. And you can also think of this in terms of area. So as the area increases, so in other words, the denominator in a fraction, so if the denominator in a fraction gets larger, then the sound intensity will be getting smaller. So the sound intensity decreases. And I noticed I made a small mistake. I should have written increases above. So once again, as the energy goes up, sound intensity goes up. As the area goes up, the sound intensity will go down. So we can think of sound intensity as how much energy is in a given area. So if we have a large room, then the sound intensity will be less because the energy needs to be spread out over a larger space. But if you have a small space, then there's more energy in a given smaller area. So that means sound intensity is higher. So that's how you can think of it in this case. Now to think about loudness, loudness is a description of sound intensity. And loudness, more specifically, we relate it to a threshold of human hearing capability. So loudness is measured as from the human capability. So they're related to humans. I think I might have spelled hearing wrong. I'm not sure how to spell that, so you have to forgive me. Human's ability to hear. There, that's one sneaky way around that. And loudness is looking at a measurement of sound intensity. So this means that if the sound intensity is high, the loudness is high. If the sound intensity is lower, then the loudness is lower, which is what we might suspect, right? Like, oh, something is really loud, we might suspect, oh, there must be a lot of energy there. So one way that we can visually see energy in waves when they're shown in a graph is through its amplitude. So let me show you what I mean by that. If we were to look at a wave with a small amplitude versus a wave with a high amplitude, which one do we suspect to have more loudness to it? Well, energy is related to the amplitude of a wave, because think about it, that displacement is higher, so that means we've got more energy to move. So if we look at the loudness as a measurement of amplitude, then we can see that the wave has more energy as the amplitude is higher. So the loudness increases as the amplitude increases. All right, and if the loudness increases, because loudness is just a measurement of sound intensity, then we also suspect that with increasing loudness, we have increasing sound intensity. So that's one way to think about loudness. Now the more tricky one is the decibel. Decibel was a unit that were derived because loudness, the numbers are too big. So the units of loudness are too big. So because the numbers are too big to work with, we want to work with smaller numbers. So instead, they're going to base a new scale of loudness based on the decibel scale, but they use the logarithmic function. In other words, we're going to be using base 10. So I'm going to explain this in more detail. So one easy way to look at it, let's say you have 10 decibels, and then you increase it to 20 decibels. So one way to look at the sound intensity or the loudness of it is it has increased by a factor of 10. Let's look at this again. Now, what if instead we have from 20 decibels to 30 decibels? How much is the loudness increased by? Not by 10, but by a factor of 10, so a multiple of 10, so by 10 times the intensity. Okay, so now let's really put all of this together. So let's start from 10 to 20 to 30. So what do we have? From 10 to 20 is times 10, and from 20 to 30 is times 10. So what is the difference between 10 to 30? So that's going to be 100 times different in intensity. So remember, if we're looking at loudness as sound intensity, and sound intensity measures the amount of energy in a given area, then if we just change by 10 decibels, we change by 10 times, another 10 decibels 10 times. So in total, if we go from 10 to 30, we change by 100 times the amount of energy. This is a crazy amount. So decibel is used because the numbers are really high for intensity of sound, and in order to discuss them, we put them in the decibel scale. Now the problem with this is that because the number is so small and people don't know logarithms, that they don't think there's much damage. They're like, oh, you know, I'm only listening to 30 decibels or 40 or 50. And they don't realize that every time they change it by 10, it's actually a factor of 10 times the energy amount. So that's a lot. So what's the conclusion here? Sound intensity is looking at the amount of energy in a given area. Loudness measures the sound intensity. And decibel is a more convenient way of talking about loudness or sound intensity because those are too big of units, so we put them in a logarithmic scale. Question 6. Oh, I hope you're still with me. I know I've been talking a lot, so make sure you put a like at least. Subscribe. If you're still with me, I really appreciate it. I have other videos you might want to learn. And if you want to see something in particular, just send me a request, and I'll be glad to make a video to help you out. Again, anything to help any physics student is a good deed to the world. So why are different units required for sound intensity and loudness? So as I mentioned, the sound intensity, the units are very large, whereas why are different units required for sound intensity and loudness. Also loudness, okay. So let's consider this by saying that the values vary very greatly. So let's look at the human threshold for hearing sound is 10 to the power of negative 12 watts per meter negative square. And something really, really loud, like a bomb, would be 10 to the power 13 watts per meter square. So again, here, watts per meter square was the measurement of sound intensity. And if you want, we can make this more friendly, just 1 times 10 or 1 times 10 to the power negative 1 to the power 13. So you see how many decimal places they must change by. In the first case, the human hearing to power negative 12, and the bomb 10 to the power 13. So there's a lot of different decimal places in between. So one way that we simplify them is to consider the decibel scale. So we're going to consider the decibel scale, which again, this particular lesson, they didn't teach you the formula, but is decibel is 10 times the logarithmic base 10 of sound intensity to the threshold of human hearing threshold. So we'll come back to the formula later. Again, you're not expected to know the formula, so it's just something a bit extra. So why are the different units required? Because the values vary too greatly and it's really hard to distinguish them unless we talk about a logarithmic scale, because they help us to determine when you move, like we said before, from 10 decibels to 30 decibels, there's actually a difference of 100 times loudness. Alright, so sound intensity, we described it as the power per area, but power is just the rate of energy flowing in a given time period. So we can think of sound intensity as how much energy is flowing through a given area. And this is due to a sound wave traveling, right? And as we said, the units are going to be the watts per meter square, but this is commonly written as watts meter negative 2. Nothing that special, we already talked about this. Now this one is a very hard question. I was surprised the first time I was doing it, so hopefully I did a good job for you. So take a moment and breathe it in. Hit a like, subscribe if you're still with me, please. Question 10. A burglar coughs with an intensity of 2.35 times 10 to the power of negative 7 watts per meter square. The burglar alarm is sensitive to an intensity of 1 times 10 to the power of negative 10 watts per meter square, and will ring if the detected sound is 30 decibels greater than its detection threshold. Will the burglar's cough be detected? So let's try to organize this a little bit. So we have a burglar, and the burglar somehow coughs inside the house, but then the alarm system is set at a certain threshold. So we want to check if the burglar's cough is below it, at the threshold, or above it. But what is the threshold? is if the detected sound is 30 decibels greater than the detection threshold. So it's a bit confusing because they're giving you the units of sound intensity and then they're giving you the units of decibels for the loudness. Very confusing. So first, let's set up a diagram to help us out. So we have the alarm and the burglar's cough. And in order for the alarm to sound off, we need to check if there's a difference of 30 decibels. The burglar's cough has an intensity of 2.35 times 10 to the power of negative 7. And the alarm, 1 times 10 to the power of negative 10 watts per meter square. All right. So before, let's go back a bit. We have a logarithmic scale. So we have 10 decibels, 20 decibels, 30 decibels. And we said that the difference between 10 to 20 is a loudness of 10 times as much. From 20 to 30 is 10 times as much. So if we're looking at 10 to 30, that would be, wait, that 100 times. But if we start off the scale at 0, let's say, what's going to be the difference from 0 to 30? Because remember, we want to make sure that it was a 30 decibel difference. So from 0 to 10 is another 10 times difference. So what's going to be the total in this case? From 0 to 10 to 20 to 30, it's going to be times 10 times 10 times 10 times 10, which is going to give us, wait, I think I put too many. Yeah, it's only 3, right? 1, 2, 3. So this is 1,000 times. Okay, let me try this again. So we don't know what the decibel reading is for the alarm or the decibel reading for the burglar. But if there's a 30 decibel difference, this means that it's changed in intensity by 1,000 times. So one way to solve this question is to check, hey, if we were to take the ratio of the two, is the ratio 1,000 times greater? Because if it is, then the burglar will get detected. So it's 0, 10, 20, 30. So let's check if the sound intensity is 1,000 times different. So all we're going to do then is we're going to take the ratio of the two values and see if it's at least 1,000 times greater. So let's take the ratio of the burglar's cough with the alarm threshold. So this gives us 2.35 times 10 to the power of negative 7 over 1.0 times 10 to the power of negative 10 watts meter negative 2. So let me calculate this. Let me double check. Okay, that makes sense. We get 2,350 times. So what was our requirement? That it needed to be at least 1,000 times, but here we got it 2,350 times greater. So in this case, it will get detected per burglar. Yikes. So it gets detected. Now, as a little bonus, we're going to use the formula to calculate decibels. So the formula they gave you before is the decibel is 10 times the logarithmic of the intensity value you're given divided by the human threshold hearing, which was 10 to the power of negative 12. So if you do this, you should get a decibel of, this one should be 20, and this one should be 53. So the difference will be 53 minus 20 will be 33 decibels. So you see it is a difference of at least 30 decibel difference. And again, this is bonus, the formula with decibels. You don't need to know it in this lesson, just as a bit extra to make sure we did it correct. Thank you for listening this far, and I hope it helps you. I know it's a long lesson, but you know what? This is a very tough topic. So see you next one.